Okay, Chemistry 3111, we were taking a look at these problems here. And the first one, we're taking this compound that has 7 carbons. Well, this is toluene. And then we're trying to convert it to this compound where we add a nitrile, right? So we're adding a carbon and a nitrogen. Okay, so we would make that from a cyanide, right? Cn minus. And then we would need an electrophile. So our electrophile would have to be this compound. Have to be this benzyl bromide, and then if we treat that with sodium cyanide, that's just going to do an SN2, and then the reaction would be complete. So how do we affect this transformation? Well, what we're going to do first is we're going to take our toluene molecule and we're going to do a benzylic bromination. So to do that, we treat it with NBS and bromosuccinimide, and that will make our benzyl bromide molecule. So makes our benzyl bromide. And then in the very last step, we're going to treat that with sodium cyanide. So Cn minus. And that's just going to do an SN2 reaction on here. And that is going to give us the product just like that. In the interest of space, I'm going to go over to a blank document for the next 2 problems. So just bear with me here as I switch over. Here we go. There we are. All right. So let's take a look here. This is 17.18. Sorry, this is D. And we're going to take this compound. So we would call this cyclohexylbenzene. So we have a benzene, and then we have a cyclohexyl group on it, like this. And then we want to convert it to this ether. So we want to make this, and then, oops, we're going to have our cyclohexyl group on it, and then we're going to have an ether on here, a methyl ether. So in terms of retrosynthesis, if we could make the tertiary benzylic bromide, so if you're wondering what do you mean by that, I mean if we could make this compound, yeah, oops, that's not very pretty, where we have the ring like this, there we go, and if we have the bromine here, then we could just treat this with methanol, CH3OH, right, and that would react via an SN1 mechanism, right, to give us the ether. So then the question becomes, well, how do we make the compound in blue? And since we have a benzylic proton on here, all we have to do is treat the compound with NBS, and that does the benzylic bromination. So we end up with our benzyl bromide derivative. So we have a bromine here, and then we also have the ring. So we'll draw the ring like that. And then to get to our final product, all we have to do is treat that with methanol. So methanol, and we are done. Okay, I should note that the book says NBS and heat. Okay, they say that you need heat to affect the the benzylic bromination. So let's move on to the last one. This is E. If we take cumene, which is isopropylbenzene, and I told you that the author of the book likes to use this compound a lot as a starting material. So if we take isopropylbenzene or cumene, notice again, since this is a recurring theme, that we do have a benzylic proton here. If we want to convert this to acetophenone, right? How would we do that? Okay, so put this here, and then if we want to make acetophenone, well, we're actually going from a compound where we have 9 carbons to a compound where we have 8 carbons. So we're losing a carbon. We don't know many ways to reduce the carbon skeleton, but one way that we could do it is via an ozonolysis reaction. If we had this alkene, right, then we could treat that with ozone followed by a DMS, and that would give us the desired ketone. So then the question becomes, well, how do I get from here to here? Well, the first step is going to be an allylic bromination. So I'll treat this with NBS, and I will heat it up this time. And did I say allylic when I meant benzylic? We do a benzylic bromination. So I'm going to end up with this compound. And then if I want to take this and convert it to the alkene, could anybody provide me a reagent for this reaction? If I want to make this compound, what would I use here? not sodium amide. I'd want to use a base of some sort, right? I'd use sodium methoxide, or you could even use t-butoxide. It wouldn't matter because it's tertiary, so you're not going to get any SN2. So yeah, I'll just pick. My students said sodium methoxide, so no problem. Sounds good. And then since it's the ozonolysis of an alkene, first step is ozone, second step is dimethyl sulfide, and there you have it. Hot dog, we have a wiener. Let's try one more that's not on the slides. Let's just try one more. This is 17.18 F. I thought this one was really interesting. If we want to take ethylbenzene, this compound, and we want to convert it to an alcohol, looks like this. 1, 2, 3, 4. So 1, 2, 3, 4. And then we have our hydroxyl here, like this. All right. So how would we make this compound? Well, in terms of retrosynthesis, I would think that you would make this from a Grignard. If you had this aldehyde, if you had benzaldehyde, then all you would have to do is treat it with propyl, right? Treat it with propyl magnesium bromide, right, in the first step, and then treat it with aqueous acid after to protonate it. And so the question becomes, well, how do you get from here to here? And it's going to involve another ozonolysis, won't it? Right? So if we take this and we treat it with NBS and we heat that up, that's going to give us the benzyl bromide derivative. And then if we want to avoid any kind of SN2, we would use a hindered base on this. So I would use something like potassium T-butoxide or DBU or DBN, and that will give you styrene. And then if you do an ozonolysis on styrene, then oops, that's going to give you benzaldehyde, right, which is the aldehyde you want. So that would give you benzaldehyde, this guy here. And then to make the alcohol, you want to add 3 carbons. First, I would treat it with propyl. Maybe I could just write it out here. CH3, CH2, CH2 minus MgBr positive. And then the second step would be to treat that with aqueous acid. So that's a Grignard reaction in the last step. So there you go. All right, so a little bit of synthesis where we need some bromination reactions. Let's take a look at the spectroscopy of aromatic compounds. So this is kind of at the very end of the chapter here. Just give me a second to find it. Okay. This section here, I'm not going to skip this with you because it was pertinent in Organic Chemistry 1, and so I think it's important now. And something that students will struggle with sometimes is where do we see the signals for carbon-carbon stretching of an aromatic ring, right? Where do you see that? Because I always find the people sometimes don't do a good job of explaining it in the textbook or textbooks. And so normally it's between, I would say 1675, or sorry, 1600 and 1475. Here they're saying 1450 to 1650, close enough. And it's generally, I would say 2 or 3 signals, with medium intensity, 1450, 1500, and 1600. That's usually what you see in an aromatic compound. And then, of course, we have the overtones, which are like 1667 to 2000. And then, of course, you have the ubiquitous, not ubiquitous, but you have the sp2 hybridized carbon hydrogen stretching, which is usually around 3100 reciprocal centimeters. So that's just a little review on that. Like, let's say you have an ethylbenzene, okay? So if we draw the structure of ethylbenzene, which looks like this, right? Here's our aromatic CC stretching, right? These are the overtones up here. And then for your, your sp2 hybridized carbon hydrogen stretching, that's going to be above 3000. And then for all of the sp3 hybridized carbon hydrogen stretching, normally we don't identify those, but those would be right below 3000. And then we can also have something called CH bending, which occurs on a ring, and some of them are in the plane and out of the plane. I generally don't ask my students any questions about those. And of course, if you're interested in NMR, and I know that most of you are, it's still important, right? That if you have aromatic protons, those usually occur or appear between 6.5 to 8 parts per million. right? And here we just see a whole cluster. So you would call this a multiplet of protons on your ethylbenzene. And of course, you have a quartet and a triplet here. And yeah, we can use spectroscopy, proton NMR, to determine substitution patterns, right? This is a really important one that I would have taught you in Organic 1. If you have para substitution, it means you're going to have two doublets, or what we call a doublet of doublets. And oftentimes they're kind of leaning in towards each other, like this, where you have one that's kind of pointing this way and one that's pointing that way, like that. So a doublet of doublets for para substitution. And then, of course, in the carbon spectrum, based on symmetry, you can determine the number of signals that you're going to get, whether you're going to have 2, 3, 4, or 6 signals, as you have shown here. I'm not going to get into Buckminster fullerene and nanotubes, and I'll leave that as an FYI portion. But graphite, if you've ever wondered about the structure of graphite, it's just a bunch of aromatic rings that are fused together. So it has a flat or planar shape, and that's why graphite makes it such a good lubricant. Anyhow, and then if you were to take a soccer ball and make a molecular model of a soccer ball, or using carbon atoms, you get the Buckminster fullerene, which is carbon 60. And again, I'll leave that section as an FYI, and also the section about nanotubes, which have a wide variety of uses, but I don't feel like I'm qualified to really go into a whole lot of details about that. You can just read the textbook, and I won't test you about nanotubes or Buckminster fullerene. All right.